cyclic voltammetry and charge-discharge curves, and we applied it mainly to capacitors. This afternoon, we're going to give a somewhat shorter lecture on a specific technique that is useful not just for capacitors and batteries, but to fuel cells and dye-sensitized solar cells, any electrochemical system. And we find it very powerful. In fact, so much so that we're going to use a tutorial, a laboratory tutorial experience for you, for the people who are on site here, to go through and actually see demonstration. And I'm going to cover just some of the basics of this technique called electrochemical impedance spectroscopy. I'm probably not going to say those long words together. I'll just say EIS. But the material here is mainly tutorial in nature, and it comes from this textbook. There's essentially a chapter in this book on EIS. So the first point is, what is impedance spectroscopy, right? And I guess it's pretty easy to break down those words. Impedance is the tendency of a system to resist the flow of charge. So it's like a resistance, but it can incorporate other types of effects, Coulombic effects, for example, that would oppose the flow of charge. And then spectroscopy is the study of some phenomenon. It could be a transport phenomenon. It could be an intensity phenomenon that is a function of a spectral quantity. Those spectral quantities can be wavelengths. That's usually what we think about. Could be energy space. It could be frequency space. But they're all kind of related together: energy, frequency, and wavelength. So that's what impedance spectroscopy is. But from a practical standpoint, what you do is you take your electrochemical system and you send an AC wave through it, okay? And from the way it responds, you can deduce many things about it. It doesn't have to be a battery. It doesn't have to be a supercapacitor. It just has to have some sort of electrochemistry involved, and you can extract it out. Now, what I'm going to tell you about are the simple circuit elements, and the way to think about devices like this from a circuit standpoint. And then when you do the laboratory tutorial, you'll see some of this in action, especially with regard to some of the effects of reactive components in a system. So the first thing to point out here is that you have a Nyquist plot. So the centerpiece of impedance spectroscopy is the Nyquist plot, in which you have a strange symbol called Z, imaginary and real. This is actually from some of the work that we've done. So I'm starting this out by kind of telling you that in this very recent paper that was published by our group, we actually use this, right? So it's a common technique. It's a little bit more advanced and certainly has a deeper theory underlying it than the things that we talked about earlier today. But essentially what you do is you look at a curve like this, and you're plotting the real impedance, the real portion of impedance, versus the imaginary portion of impedance. And hopefully what you'll do through the process today in this lecture and in the tutorial exercise is you'll kind of understand what those impedances stand for, or maybe even within part of this Nyquist plot. So the way to measure this, there's a couple of different techniques that you can use, or kind of circuit forms that you can use. On the left, you have a bridge circuit. You might have seen that before. A bridge circuit is something that tries using variable components like variable resistor and capacitor to balance out voltages within itself. And so it can send current from one side to the other, so that at the end, you can easily measure the voltages that are coming out of your cell, and you use an AC source to drive all of this, and you can look at the response of your device to different frequencies of an AC source. Another slightly different way of doing things is called AC voltammetry. In this case, you have a DC background with a AC wave on top of it. And you can do essentially the same kinds of things. You end up using lock-in amplifiers and low-pass filters in this case to achieve your frequency response, to understand your frequency response. So the lock-in amplifier, if you don't know what that is, that's something where you can choose a frequency and get the signal out at that frequency. Okay, so very simple things here. When we talk about entities in the frequency domain, we usually go quickly into sines and cosines, right? And then sometimes those sines and cosines turn into complex variables. And indeed, that's what we'll do. So you can look at this in phase space. That's E and I. There's an E vector, an I vector, or E dot and I dot. I won't use the terminology too much, but you could represent this E and I as a couple of sine waves that are offset by a factor phi. Okay, so that's the phase difference phi. So if we use the E signal, the voltage signal, E is voltage here. I'm using the nomenclature from this book, so sorry to confuse you, but I'm using the nomenclature from the book. If we use the voltage signal as the primary definition of time, then what happens is you get your sine wave, and then your system, for whatever reason, reasons that we'll describe later, responds with some delay, with some phase lag, okay? And that phase lag is all captured in this term phi. You can represent sines and cosines in a complex plane with using complex variables, and that's what this phase or phasor diagram shows, the circular entity. So what if we just had a pure resistor? What if our circuit was a pure resistor and we wanted to do some kind of frequency response analysis of that? It's the simplest thing, I think, that you could do. Well, what you have with pure resistance is there's nothing that can that can cause a phase lag in a perfect resistor, and so your current response would have the same phase as your voltage input in that case. Okay? So then my phasor diagram would have these vectors in the complex plane lined up on each other. Easy, right? As simple as it can be. If I have pure capacitance, on the other hand, then I end up finding that the phase difference between the current and between the voltage and the current ends up, they're 90 degrees out of phase. The current ends up being a cosine function, which as we know is 90 degrees out of phase with the sine function, and so you have a phase lag of pi. Now in this case, I think we're accustomed to working with resistances, and when you have a resistor, you have V equals IR, right? And so it's really easy. They're related by resistances. Or in this case, I equals V over some new factor that's called X sub C, which is the capacitive reactance. Okay? It's like a resistance. Okay? But this capacitive reactance is something that's important. It is frequency dependent. And that's going to become important as we look at analyzing these materials, because I could actually tune that out. I can tune that out in a real circuit by essentially making this X sub C become negligible by going to very high frequencies. Because when I go to very high frequencies, that reactance will go to 0. And we'll see how that affects things in some of the impedance spectra that we look at. If I have a resistor and capacitor in series, okay, so this is one after the other, then I get a combination of the two effects, and we end up seeing that the voltage is equal to the current times a resistance minus a complex term that comes from that reactance, that capacitive reactance. Okay? J here is the imaginary number. And I will note that in the development that we're showing here, we're using a minus sign on the reactance component. Not all of the textbooks will do that. Sometimes they'll use a positive sign, just, I guess, to avoid confusion, in which case everything is just sort of flipped. But the reason that the negative sign is used here is that the current, right, is the electric field is phase lagged by 90 degrees behind, and so you end up with it's easier to imagine it than in your Nyquist plot. Your imaginary component through this definition is always positive. Okay, so that's why it's done. Now, if I have a resistor and capacitor in series, then if I plot the imaginary impedance versus the real impedance, what I'll get is a vertical line, because remember, now I have one of these terms that depends on frequency. Okay, so now I can create a curve between these two. And it's important to recognize what's happening here. If I had a circuit, again, resistor and capacitor in series, with a 100 ohm resistance and a 1 microfarad capacitance, I'd get a vertical line. And as the frequency goes to infinity, I mentioned that before, as your frequency becomes very high, you're essentially canceling out the capacitive reactance part. And so you go to the intercept of the real curve, and you should get the real resistance. And indeed, in this case, that's what you would find. Your resistance, your real impedance, the real component of impedance would be 100 ohms. Okay? So that's one of the extremes that we use in electrochemical impedance spectroscopy, the high frequency limit, to show, you know, that we're some kind of sanity check on the actual device that we're testing. The other part of this is that as frequency decreases and we get to low frequency, then you see a vertical rise. So the imaginary component comes up. The real part doesn't change. That imaginary component comes up because that reactance term is becoming larger at low frequencies. And then it just rises up. Now, you'll rarely see an impedance spectrum that looks like this, because you're usually not testing perfect linear circuit elements. There are other things going on, right? And that's why, and in fact, you'll rarely have things that are perfectly in series. Most of the time you have distributed resistances and capacitances that end up being in parallel. So let's take a look at a more general circuit. So generally speaking, what we have is we can add these impedances like we add resistors. That doesn't mean they always just add together. What I mean is, if they are in series with each other, then you add in series like you add resistors. If they are in parallel with each other, you add them as if they were parallel resistors. Okay? So that makes it a little bit easier, because you probably know that if I have two capacitors, I hope you know this by now because we've mentioned it a few times, if I have two capacitors in circuit series, then they add like resistors in parallel, and vice versa. Okay? So this way, by casting everything into the impedance framework, then we're adding resistors, we're adding impedances the way that we add resistors, which is more familiar to most people, certainly to mechanical engineers like me. Okay, so what if we have a parallel RC circuit? This gets a little bit more interesting. I think straight lines are boring. All right, this gets a little bit more interesting. We now have a resistor and capacitor in parallel, and pay attention to that top element there. That's the frequency. The frequency is going from low to high, from right to left. Okay, so the very high frequency here, frequency going to infinity, is actually coming down to the origin of the curves. So as I go to infinite frequency, what's happening in this parallel model? Well, infinite frequency, I have zero impedance, imaginary impedance, and zero real impedance. Does that mean that I don't have any resistance anymore? I mean, what does it really mean? What it means, and the way I think about it, at least, is that you end up having a circuit. Your circuit cannot respond fast enough when the frequency is infinite. And it's oscillating up and down, positive and negative. It's bipolar. It's a bipolar source. There's no DC component to it, right? That circuit cannot respond fast enough to your AC signal at some point, and it just sits there and takes its own average. And the average of an AC signal that's bipolar is 0. So that's what it feels like to that circuit. As you go to very low frequencies, though, again, this is the same circuit elements that we had before, only now they're in parallel. As you go to very low frequencies, you would hope that the circuit would look like a 100 ohm resistor, right? That capacitor is not going to charge very much because the electric field, the rate of change of V, remember dV dt, right? That dV dt is going to dictate what your current is in the capacitor, and if dV dt is really small, then, well, the capacitor is not really going to be doing very much. So as I go to very low frequencies, I would expect to see really just a resistor. And indeed, that's what we have here. We have a 100 ohm resistor. Now, in a lot of interesting electrochemical systems, you will see a feature